Hi, my name is Sarah.
My name is Zoe Jen.
I'm Steven.
I'm Winifred, and this is the vapor-liquid equilibrium experiment. The objective of this lab is to determine the vapor-liquid equilibrium curve of 2-ethoxyethanol and water, and from this data to determine the binary activity coefficients.
In this experiment, 2-ethoxyethanol and water will be used. This is a bouilliometer system. This is a condenser, and this is a main chamber. The valve right here will be used to collect the gas sample. The valve right here will be used to collect liquid sample. This is the main switch. You will be use this switch to turn on or turn off the system. This is the lamp indicator. When the system is on, the light will be on. This is the display screen. You will be record the temperature from this screen. The green button will be used to start the heating. The red button will be used to turn off the heating. This is the water bath. You will be connected to the condenser, and you will be used here to adjust the temperature. These are sample vials, and these caps. You will be use them to collect the samples. This is the hot plate. You will be use it to heat the water. This is dial barometer. You will be used to measure the atmospheric pressure.
Before starting the lab, make sure that a TA is present. The first thing to do when starting the lab is measuring the atmospheric pressure using the barometer. You will also take a pressure measurement at the end of the lab to make sure that there is no dramatic pressure increase or decrease during the duration of your experiment. Heat some water for use later in the lab. To do this, add a beaker to a hot plate and a magnetic stirrer as well as some water. Turn on the hot plate as well as the magnetic stirrer. We do this when we're adding water to solutions, and we use hot water in order to not fracture the glass of our apparatus. Afterwards, turn on the cooling bath to 20 degrees Celsius and make sure that the flow control is open. Perform calculations for 10 decreasing concentration solutions of 2-ethoxyethanol. Once that is done, come over to the apparatus and ensure internal circuitry in the glass casing and place beakers underneath the valves in the case of leakage. Then come over here and turn the main switch on by rotating it clockwise, after which the white light will turn on, and adjust the power level to 75% and click the green button. Wait 5 to 10 minutes for the apparatus to heat up. The solution will begin to boil and establish internal equilibrium. Condensation will begin to occur, and the temperature will begin to stabilize. When you see that your temperature has stabilized, record the probe temperature and the water bath temperature and record it on your data sheet. And then proceed and repeat the process for your next solution. Also, remember to take one duplicate sample so that you can calculate errors and standard deviations.
When you're finally ready to take your samples, open the cabinet to the system, and then start by draining 15 milliliters out of each valve. Save this liquid as it will be recycled after the sample is taken. The reason we recycle that fluid through is to clear the line so we get a pure sample. We're going to do the same thing with the distillate. Once you've taken your sample, you're going to want to cap it as soon as you've taken it, just to ensure that there's no vapor escaping. Once you're done taking the sample, make sure to return your valves to the original position so the system maintains steady state. Then turn off the system so you can add more fluid. Wait for the bubbles to stop being produced in the column, meaning no more vapor is coming off the top. So then you can open it up and pour in the rest of the fluids.
Each sample is then analyzed using a refractometer as laid out in the composition analysis booklet. If the reading is above 1.3900, the solution must be diluted.
Once our system has stopped bubbling, and we can see it through the slit on the glass in the front, we can then open the apparatus back up and unscrew the thermocouple at the top. Once this is unscrewed, we use a funnel to then recycle our previous streams and to add the water to continue diluting our solutions. Once the water's added, we're going to want to remove the funnel, put the thermocouple back in, ensure our flow paths are correct in our system, and then turn on the heat again. For our 10 separate trials, we're going to have to differ the concentration, and that involves diluting the solution that's in the equilimeter. What that entails is that we're going to have to drain excess fluid out of the equilimeter so it doesn't overflow. That's done simply by using the bottoms valve and emptying a certain amount that you've already measured based on your data sheet out of the system, and then diluting it with the proper amount of water at the top. Once you're finished taking samples, turn off the heat to the system. Let the system cool slightly before draining out the fluid.
To shut down this experiment, first you're going to remove the temperature probe or the torion and fill the equiliometer with 300 milliliters of heated water and turn on the heating source. Then you wait 15 minutes for the water to circulate and clean the inside of the apparatus, and then empty out the water, put it in a beaker, and flush it down the sink. Afterwards, once the water bath has cooled down to less than 30 degrees Fahrenheit, you'll turn off the water bath and turn off the power source, and you're done.
After we've added our water, we're going to want to check that our liquid level is between this mark here and this valve here, which right now, it's right here.
One of the tips to run the lab is to analyze the sample quickly, avoid the evaporation. To do this is to cool the sample in the water bath. In the vapor-liquid equilibrium experiment, repetition and randomization will be used. When collecting data, there will be one concentration replicate. This replication will help to determine the position and the reproducibility of the VLE data collected and the activity coefficients generated. Randomization is used when the replicate concentration was chosen at random.
There are various hazards present in this lab. The first is a broken glassware hazard. If any glass breaks, wear gloves and carefully collect the broken pieces and dispose of those pieces in a broken glassware container. The second hazard is a liquid spill hazard. If a liquid spill were to occur, turn off or control the source of the spill and wipe up small spills with a paper towel. In case of a large spill, mop up and set up a wet floor sign. The next hazard is a burn from hot surface hazard. Avoid contact with the hot surface, and in case of a burn, run cool water over the burn until the pain is gone, and cover with a loose bandage. Seek medical help for more serious burns. The next hazard is an electrocution hazard. Be careful when turning on and off switches and when plugging in and unplugging equipment to make sure that your hands are dry and you are not standing in a puddle. Also, do not touch prongs when plugging in and unplugging equipment. Our next hazard is the pinch point hazard. And in the case of a pinch, treat injuries with a first aid kit present in the lab. The chemical 2-ethoxyethanol used in this lab poses some serious health hazards to the participants of the lab. First, it is flammable. It is also acutely toxic, an irritant, and a health hazard. For these reasons, we wear proper PPE, including nitrile gloves, and also use caution when handling the 2-ethoxyethanol chemical.
Although there are no noise hazards during our lab, you might want to wear earplugs due to other labs that do have noise hazards.
The index of refraction measurements will be converted to mass fractions using the calibration curve provided in the lab. The mass fractions for the diluted samples will be solved for by using both the calibration curve and a stoichiometric equation which relates the sample masses and mass fractions. All mass fractions will then be converted to mole fractions using each chemical's molecular weight. The equilibrium ratio, or K value, is a measure of the tendency of a chemical to concentrate in one phase over the other. If K is less than 1, the chemical has a higher concentration in the liquid phase. K values will be calculated by dividing the vapor phase mole fraction by the liquid phase mole fraction. This will be done for both water and 2EE. The relative volatility indicates whether or not an azeotrope exists. If alpha is equal to 1, an azeotrope is present. Alpha values will be calculated by dividing the K value of water by the K value of 2EE. The activity coefficient is used to indicate deviations from liquid phase ideality. Saturation pressures will be calculated using Antoine's equation at the recorded temperature of equilibrium. Activity coefficients will then be calculated using the modified Raoult's law, shown on the right. Thermodynamic consistency will be tested for using two methods according to the Gibbs-Duhem equation. For the differential method, the natural log of the activity coefficients must be plotted versus x1 and fit with polynomial equations. The polynomials can then be analytically differentiated and used to solve the equation. For the data to be considered thermodynamically consistent, the average absolute value of the left side of the equation must be less than 0.10. For the integral method, the natural log of gamma 2 divided by gamma 1 must be calculated and plotted versus x1 and fit with a polynomial equation. The polynomial can then be analytically integrated and used to solve this equation. For the data to be considered thermodynamically consistent, the value of the integral must be equal to 0. If the experimental data are thermodynamically consistent, the activity coefficients can be modeled using both the Redlich-Kister and Van Laar models. For the Redlich-Kister model, gamma and x values are plugged in to solve for A, and A is an average to find the Redlich-Kister parameter. For the Van Laar model, A12' and A21', the Van Laar parameters, can be calculated using a nonlinear least squares regression after calculating both the left and right-hand side of the equations.